Today's topic is a return to arc length, which we discussed before, but we're going to do it with a little different notation and do some neat geometric applications of it. We've done vector valued functions and they sweep out curves. Now what we want to do is think about, as you move along a curve, what is a coordinate system that moves along with you? How sharp am I turning? How far have I gone? We're going to answer those kind of questions today with calculus. Previously we had a smooth curve. That means a curve with at least one derivative for the components, right? X equals x of t, y equals y of t, with their first derivatives continuous at least, maybe more. On some interval, maybe a to b. And we've derived this arc length formula that s is the integral from a to b of the square root of dx dt squared plus dy dt squared. Now, we're going to introduce some new notation is what we're going to do. We had a parametric curve given by x equals x of t, y equals y of t. Let's now also describe it as what we call in physics a position vector, r of t, equals x of t I plus y of t j. This is a vector at the origin that points to the point x of t, y of t. So its terminal point sweeps out the curve. And now with this new notation that we introduced, we can say that the arc length is actually the integral of the length of r prime. This is a whole lot easier to remember, I think, right? It's kind of like integral of velocity is position, right, from calculus 1, but now you've got more dimensions. In more than one dimension, you integrate the length of the velocity vector, right? If t is time, r prime is the velocity. In any case, it's called the tangent vector because it's tangent to the curve. We integrate the length of the velocity vector to get the distance traveled. Is the idea there. But this is just notation for this, right? Because r prime is dx dt, y dt, that vector, and so its length is root sum squared of dx dt and dy dt. So this is a nice way to remember the arc length that we saw before in terms of our new notation of position vector from the last section. Consequently, the arc length from t equals some initial point A that you pick to an arbitrary t is, well, instead of going from A to B, you just go from A to t. And then just to avoid a mathematical faux pas, you're not really supposed to put t in here if you put t at the end point. So we'll change the dummy variable to tau. It doesn't change anything, right? I could just as well call this r prime of tau d tau, and it would be the same value because this variable, the independent variable here, falls out when you evaluate it at the endpoints. So we'll evaluate with using tau instead of t. It's the same thing, and then we'll plug in t and plug in a and take the difference. So it's this integral from A to an arbitrary point t. It's the arc length along the curve, swept out by these parametric equations, x equals x of t, y equals y of t, put it in this form just for different notation. And now, however, an interesting thing occurs. You realize from the fundamental theorem of calculus, one of the two parts, remember this one, maybe I can put it up here real quick. Take the derivative with respect to t of an integral from a to t of f of x dx. One part of the fundamental theorem of calculus said this is equal to f of t. Excuse me. Actually, let's use f of tau d tau since it's our notation today. Was f of t, and it just said the derivative and the integral undo each other and give you back the function, except now I evaluated at t instead of at tau, and the derivative undoes the integral. If we apply that fundamental theorem to what we have here, the derivative of the length of r prime of t, the derivative of the integral of the length of r prime is just the length of r prime evaluated at the new variable t, fundamental theorem of calculus. So, the derivative of position, or arc length, is equal to the length of the tangent vector, or velocity vector. Written in the other notation, this is ds dt equals length of dr dt, or sometimes we'll call that v of t, the speed as we move along the curve. And so v with an arrow over the top means the velocity vector. It has components, but the little v without an arrow over the top means the root sum square of the components of the velocity vector that we call the speed. we consider a parameterized curve C, we say it's regular if it is smooth, that's one continuous derivative, with that derivative never equal to 0 along the curve. In this case, what we find out is dS dt, which we just showed was equal to the length of dr dt, must be positive because dr dt is the zero vector. So s of t, that means it's increasing. If the derivative of s is always positive, then s must be an increasing function, being its integral, right? And so, if it's an increasing function, remember an increasing function on an interval is invertible, you can write t as a function of s. So for a regular parameterization, we can take that arc length parameter that we just defined as an integral and invert s of t to write t as a function of s. And then dt ds, because this is a smooth curve, is just 1 over ds dt exists, ds dt not being 0. And by the chain rule, then we have derivative of r written as a function of parameter t, written as a function in term of the arc length s with respect to s, is dr dt dt ds by the chain rule. And by the way, how do we know this chain rule works? Well, remember you take derivatives component by component. The chain rule works for each component. And so this just, you just apply the chain rule to each component and you get this rule is what you get. That's the proof of it. So the chain rule for, from calculus 1 extends to vector valued functions where r is a vector valued function of the function t of s is dr dt dt ds. And now r of t of s is now written as a function of s. It's written as a function of the arc length. For that reason we call s the arc length parameter. It's the new parameter that measures how far we've gone along the curve. R of t of s, or just r of s, gives you how far, what position you're at when you moved along s units along a curve. Here's a nice example. I'm not going to get real detailed in this section. Suppose the arc length, we want to find the arc length of the curve r of t equals cosine cubed ti plus sine cubed t j, that's 3, along the interval 0 to pi over 2. I wonder what the arc length could be along that curve. First of all, we recognize it's a smooth curve. How do we know that? Each component has a continuous derivative, right? Cosine is a differentiable function with a continuous derivative, and so is the cube function, and the continuously differentiable function of the continuously differentiable function has a continuous derivative. Same thing here. So the components are continuously differentiable functions, smooth functions. By the way, be careful of that term smooth. In calculus, it usually means it has a continuous derivative. In that way, we avoid here if we have a corner in a function, then there's a point at which the derivative doesn't exist, it fails to be smooth, right? But if it has a continuous derivative, then it won't have any corners in it. So that makes sense in calculus. In higher mathematics, it often means as many derivatives as you need for the application. It might mean it has at least 2 continuous derivatives in a physics problem where you're worried about acceleration and so forth. Or it might mean in lots of higher mathematics, tensor analysis and so forth, often smooth means it has an infinite number of derivatives, all of them automatically continuous. Since if you differentiate it again, it's automatically continuous. So smooth can mean different things. In elementary calculus, first and second year calculus, it normally means one continuous derivative. That's what we'll mean here. S will now be, if we want to calculate the arc length along this curve, integrate from the beginning of the parameter 0 to the end value of the parameter pi over 2, square root of dx dt squared plus dy dt squared. Well, the derivative of cosine cubed by the chain rule is 3 cosine squared times derivative of cosine, right, by the chain rule for this one. By the chain rule for this one, it's 3 sine squared times derivative of sine, or 3 sine squared cosine. So we have the first component squared of the derivative squared plus the second component of the derivative squared, square root integrated with respect to t. There's a dt off the end here. If we look at it for a second, square of that is 9 cosine 4th t squared. This one is 9 sine to the 4th cosine squared, and you can factor out a 9 sine squared cosine squared from both these terms, all times cosine squared here and times sine squared here. So we got 9 sine squared cosine squared times cosine squared plus sine squared, but I scratch that out and put equals 1. This is all just the square root of 9 sine squared cosine squared. Square root of 9 is 3, square root of sine squared is sine, square root of cosine squared is cosine on the interval 0 to pi over 2. You have to be careful on another interval, maybe it's minus these. Oops. Alright, so we need to integrate this to get the arc length. But sine t times cosine t, that looks familiar, right? 2 sine cosine is the sine of 2t by trigonometry, so this must be the 1/2 the sine of 2t by trigonometry, right? Sine of 2t is 2 sine cosine. So this is 1/2 sine of 1/2 sine of 2t. Alright, so we can write this as 3/2 then, integral of sine 2t, integral of sine 2t is cosine 2 minus cosine 2t over 2. So we get minus 3/4 cosine 2t. Plug in the endpoints and take the difference, you just get 0 on the top and minus 3/4 on the bottom for 3/4 overall. So there's the arc length, it's 3/4 units as we move from 0 to pi over 2. Now, if we can find the arc length, presumably we can do that integration, we must be able to find the arc length parameter, right? The arc length parameter, s, or s of t, is the integral of r prime of t, tau, d tau, recall. That was our previous result. And we can use part A, right? In part A, we found out the antiderivative of the length of r prime of t was minus 3/4 cosine 2t, so we'll just do that here, but put in tau. And then we have to plug in t and 0 and take the difference instead of 0, pi over 2 and 0. So it's the same integral as before, just take them from 0 to t instead of 0 to pi over 2. Now, at this end, it's minus 3/4 cosine t, and this one end it's minus 3/4, so the minus in front is subtracting negative 3/4 minus 3/4 cosine 2t is the arc length at any point t along the curve. So at t equals 0, we've got arc length 0. The reason is if you take the arc length parameter from 0 to t, notice this is the thing that measures off arc length with arc length at t equals 0 being nothing, right? If we put in t equals 0, this is the integral from 0 to 0, so the arc length, if you're at 0, is nothing. This says we've gone this many units past t equals 0 to get to the current point we're at. Now you can also go backwards to a negative number. If you do, then you get a negative result. It becomes minus the arc length back to the position you're at. So this is the arc length parameter as we move along the curve from 0 to pi over 2 in this case. Suppose we want to write the arc length parameterization of the curve. That is, write the position vector r of t as a function r of s of the arc length you moved along the curve. We said you could do that by finding the arc length parameter s, inverting it to write t as a function of s, and then plugging t into r. That's all we have to do. It's 1, 2, 3. Invert, 1, solve for s of t, 2, invert, and 3, substitute that inverted formula for t. So we've already done this part. We've got s, the arc length parameter s. How do we invert this equation? S equals 3/4 minus 3/4 cosine 2t. It's just algebra and trigonometry, right? Right, s. I scratched off the of t here because I'll just write s equals this. And I'll subtract s over and add 3/4 cosine 2t to get this equation. And I'm trying to solve for t, so I multiply by 4/3, getting 1 here and minus 4/3 s here. And now I'll take the inverse cosine here, which I can do for this interval t between 0 and 2 pi, pi over 2. And then divide by 2, and here is t written as a function of s, which was valid on t between 0 and pi over 2, and consequently, if you look at the formula for s moves between 0 and 3/2 as t goes from 0 to pi over 2. So this is t as a function of s going from 0 to 3/2, which is the arc length of the curve. So now, once I find t as a function of s, I just plug it into r. r of t was cosine cubed t plus I plus sine cubed tj. Just for t, we put this formula in, and we get cosine cosine cubed 1/2 arc cosine 1 minus 4/3 s plus times I plus sine cubed is the same times j. All right, so that's writing the position vector as a function of arc length. If I've gone 10 units along the curve, and I'm plugging in s equals 10, I can find out what's the position when I'm 10 units along the curve. All right, now, just as a follow-up, we mentioned the chain rule. Find dRd tau by the chain rule of RT is Ti plus T squared J. Well, I just write the chain rule as dRd tau equals dRd T dt tau. And so if R of T is this, and T in turn is 3 tau minus 5, dRd T is I plus 2 Tj taking the derivative of this with respect to T, right, dRd T, plus dt tau is just 3, so we multiply the whole thing by 3, and the chain rule says 3I plus 6Tj is dRd tau at any position along the curve. So there's the chain rule just for a fun example. Now, having done that, we've got arc length down and the arc length parameterization of a curve. Here's something else that's useful, unit vectors as you move along the curve. It's illustrated down here. Suppose I have a curve C, here's x, y, and z, and the curve C moves around like this. And I'm at some position along the curve. We can get actually a coordinate frame. Instead of I, j, and k vectors, when we're sitting at this position, maybe we want some position-oriented coordinates that the origin is at our position, and maybe we want the x-axis to point in the direction we're moving, so it's like we're driving a rocket ship around and x is straight ahead. And then I'll put another, instead of j, I'll put this little vector n out my left-hand side, and then b will be up. And maybe this is like aircraft dynamics or something. And so you got a forward vector, a left vector, and an up vector. As I move along this curve in my aircraft, and these might be a convenient coordinate system where I'm at, as opposed to I, J, K, where I'm moving around in space and I is always changing with respect to the direction I'm moving. How can we find these unit vectors, 1 unit long, T, N, and B, called the tangent vector, normal vector, and binormal vector? Here's how you can do it. Remember that R prime is tangent to the curve. We called it the tangent vector for that reason. How can we find a unit vector? Just divide it by its length, right? Any vector divided by its length becomes a unit vector 1 unit long. So the unit tangent vector is defined to be R prime of T over length of R prime of T, along a regular parameterization where R prime is never 0. All right. So that gives us our tangent vector. How can we find a normal vector? I bet you wondered last time why I bothered to put this silly theorem that if you have a vector that maintains a constant length, but just changes its direction, it's perpendicular to its derivative vector, right? We did this neato proof and didn't do anything with it, right? Now we get to do something with it. It's just like in algebra, you said, what is all this stuff good for, right? And it turns out in trigonometry and calculus it's very important, but you don't see it right away. Same thing here. Here's a nice illustration of the way a lot of books like to place this. If you have a vector, whatever, v or something, and it's a constant length, r or something, and so then it turns, and it says a vector placed at the origin, then it turns and its terminal point is always along a circle of radius r, if it's a constant length r, right? And now, so what does its derivative vector look like? Remember that the derivative is tangent to the curve it sweeps out. Well, if it's moving along a circle, then its derivative has to be tangent to the circle and the derivative in the direction of increasing t. So, when we have a vector of constant length, its tangent vector should be perpendicular to it because it goes from the origin to a circle and the derivative has to be tangent to the circle. This is a nice geometric way of thinking of it. The proof we did last time, we used the dot product, if you recall. So the proof is kind of nice like that, but this is so intuitive. I love this illustration. Now with that in mind, that a vector that maintains constant length is perpendicular to its derivative, we go and look and say, wait a minute, t is a unit vector. It has constant length 1. It just changes the direction it points. So if we just took its derivative, t prime, that would be perpendicular to t. Well, we'll take t prime divided by its length and get a unit vector perpendicular to t and call that the unit normal. So The unit tangent vector will be r prime divided by its length, since r prime is the tangent vector. The unit normal vector will be t prime divided by its length. Don't put r double prime over the length of r double prime, that doesn't work. You might think it does in this formula. But that's because t has constant length and is perpendicular to t prime. Now in 3 dimensions, this works in 2 dimensions, that's all you need in the plane. What if you're in 3D, like this problem down here, you need a third coordinate that's perpendicular to the other two. Piece of cake, right? Remember the cross product is the vector that's perpendicular to the two vectors you put in. So if I put in t and n and take their cross product, the vector b, that's the cross product, will be perpendicular by the right hand rule. You take your right hand and point it in the direction of t, turn it towards n, and your right thumb, using your right hand, points in the direction that b will go. And then how long is b? Remember this formula? What is the length of b? Well, it's length of t cross n, since we define it that way. But by the cross product formula we had, it's length of t, length of n, cosine of the angle between them, but they're at 90 degrees to each other, right? They're perpendicular. So cosine, sine of 90 degrees. Sorry, put it at the top. Sine of 90 degrees, and the sine of 90 degrees is 1. N is a unit vector, its length is 1. T is a unit vector, its length is 1. So the length of b is 1, because it's the cross product is perpendicular by the right hand rule. It follows that b is precisely the vector we want for a right-handed coordinate system. X followed by y goes in the direction of z. Remember, in 3 dimensions, you can also have left-hand coordinate systems where you take t cross n with your left hand, and then not cross, but use your left hand, turn from t to n, and the vector would point down. And that's very seldom used in textbooks. Almost everybody uses right-hand coordinate systems. I've seen Russian aircraft use left-hand coordinate systems. It's convenient for orienting up and down, so for instance. But this is really what we want as a right-hand coordinate system for all our theorems that we have in the book. And so we define t, n, and b this way. Now we have a unit vector system that can move along with the body, right? Because we plot r prime, and hence t is r prime divided by its length, at the point where r goes. So r comes out to this point along the curve, as we're sweeping along the curve. R of t, the terminal point, is at the curve, and then t points tangent to there. N points perpendicular to that. What direction does it point? It turns out that it points in the direction of acceleration. If you look at this formula, we won't go into the details here. It turns out that n lies in the plane of r prime and r double prime. And so it's always in the velocity acceleration plane. Since t points in the velocity direction, n points within the plane containing velocity acceleration on the acceleration side. So if you're turning this way around the curve, n will point inward. If you're turning that way around the curve, n will point out that way. That's how it works. And then b is always perpendicular by the right-hand rule. All right. Now, finally, curvature. If t prime and r prime, double prime exist, the curvature can be defined to be, it's hard to see here, kappa, Greek letter kappa, equals the length of dt ds. Well, t is a changing length, so dt ds is telling you how fast the unit tangent vector is turning, right? And so kappa is a measure of how fast you're turning. It's the rate of change of t with respect to the arc length. Well, that's a very difficult calculation. You saw how hard it was to calculate a function of the arc length parameter. In general, it's actually harder than what we showed. The integration is either hard or you can't invert the result you get. So this is a really hard calculation in general. We just picked an easy cooked problem on that one. Otherwise, trying to calculate kappa, it can be quite difficult. So what we do instead is there's another formula for it. This is the computational formula. You can show that length of dt ds, the rate of change of the tangent vector with respect to arc length, is actually equal to the length of r prime crossed r double prime over the length of r prime cubed. Now immediately you notice this is in 3 dimensions. We've been doing all our problems up to this point in 2 dimensions. But I said you can do all these things again in 3 dimensions, and then you have this third vector b. So you compute this in 3 dimensions, but if you're in 2 dimensions, all you do is you embed your r prime, and r double prime in the plane into 3 dimensions by adding a third component 0, and then you can use this formula to calculate curvature in the plane also. Alright, so here's the example of that, and I want to point out one more thing. What does the curvature mean? What's its significance? Here it is. If you calculate this for a circle, you'll find out that 1 over the curvature is always the radius of the circle. We're going to show that here for a circle of radius 2. If 1 over the curvature is the radius of the circle when you're going around a circle, which in some sense curves at a constant rate, then we'll define rho to be 1 over the curvature, call it the radius of curvature, and it's the radius of the circle that just fits the turning rate of the curve. So here's how we can calculate using the computational formula. Suppose I have a curve x equals 2 cosine t, y equals 2 sine t, t going from 0 to 2 pi. We recall that's a circle of radius 2, traversed counterclockwise. R prime of t is just the derivative component by component. So it's derivative of this one minus 2 sine t, derivative of this one 2 cosine t. And then t, the unit tangent vector, is r prime divided by its length. So it's minus 2 sine, 2 cosine divided by the root sum square of those two things. But the root sum square is 4 sine squared plus 4 cosine squared is 4, and square root of 4 is 2. So this is all just minus 2 sine t, 2 cosine t over 2 is minus sine t cosine t. There's the unit tangent vector. You can see it's a unit vector, right? This square plus this square is 1. So it looks like we made the calculation correctly, right? Now the unit normal is the derivative of this vector, t, divided by its length. So we take its derivative and get minus cosine minus sine, divided by its length, which is the root sum squared, cosine squared plus sine squared. Oh, the bottom's 1, so the unit normal is just minus cosine minus sine. Finally, the binormal, we just take their cross product, t cross n. Well, these are vectors in the plane, 2 components, so we just append zeros on the end. And we take the cross product, and we get, well, not surprisingly, since it's in the plane, a vector in the direction k upwards, right? We're moving around in the xy plane down here, and we take a cross product of 2 vectors in the plane. It's going to point in the z direction or the minus z direction. And what you get taking this cross product is sine squared t plus, right, it's k times this minus this times this is sine squared plus cosine squared times k. It's just k. It's a unit vector upward, obviously a unit vector, right? And so here's your TNB frame, they call it. And the special planes have special names, just like we have an XY coordinate plane. You have a tangent plane, and some other names, special names for the other 2 planes. I've forgotten, osculating plane. Anyway. Now here's the picture. We're moving around this circle of radius 2. R of t points out to some point on the circle. The unit tangent vector, so this is radius 2, the unit tangent vector is then half that long pointing tangent to the circle in the direction you're moving, so it points this way. The unit normal is perpendicular to that in the direction of acceleration. You're turning this way, so it's a unit vector pointing back this way without even calculating. You can put this in at, say, pi over 4 or something, looks like about pi over 4, and compute this and see, but without even plugging in the point. I know it's going to point towards the origin, perpendicular to the tangent vector, and then b is going to be t cross n is going to come out of my paper. And there's my TNB frame for moving